Case study 7.1 looks at the electrochemistry of batteries. And of course, chapter 7 in this course looks at electrochemistry, and one of the most remarkable transitions is that a few years ago, electrochemistry, which is always an interesting subject intrinsically, moved to the forefront of huge efforts in chemical research, because the chemistry of batteries, it turns out, is one of the most important developments in the evolution of renewable energy globally. So case study 7.1 looks at the electrochemistry of batteries, and actually starts out with the history of batteries. And the oldest battery was discovered in Baghdad, Iraq. This was the first battery ever created by humans, as far as we know. But when we look at batteries in a broader sense, we have three categories. We have primary cells, and this refers to batteries that have a chemical reaction that produces the flow of electrons, but it's an irreversible chemical reaction. That means you cannot recharge the battery. Secondary cells, in sharp contrast, engage a chemical reaction that can be reversed, and it's reversed by applying a voltage backwards into the cell itself, reforming the reactants in that electrochemical reaction that can then be used again and again and cycled through discharge charge cycles. And finally, fuel cells convert chemicals into electricity by using those in an anode-cathode combination. And we've talked briefly about that with respect to fuel cells that use hydrogen to produce electricity. But when we analyze batteries, and we'll just quickly summarize here, it's important to start out with the lead-acid storage battery, because this battery has been around for 150 years, and it's still the battery that starts your automobile engine in the morning. But it's a secondary cell because its primary reaction that develops the voltage required to drive electrons through the external circuit that then drives the starter motor can be reversed by applying a voltage in the opposite direction to the battery. And that's what the alternator on your car does. When you're driving, that alternator is pumping electrons back in the opposite direction, and it maintains the charge of the battery, so the next time you need to start the car, the battery operates, and the battery will go through these cycles for a period of years before it's exhausted. Another very typical battery is the alkaline battery. Now, this is the standard battery that you buy in D and C sizes, and AA and AAA. And as everybody knows, these batteries go dead. You have to recycle them, but they are pretty inexpensive and fairly lightweight, and they have a typical output voltage of about 1.54 volts, 1.5 volts per cell. So alkaline batteries certainly count in analyzing it. And one of the things we always look at in electrochemistry is what is the net overall reaction that occurs to drive that voltage. And that's one of the most interesting things to keep our eye on in this case study. So in this case study, when we're analyzing batteries, we step through increasing sophistication in the battery structure. And the next very important category involves the nickel metal hydride cell. And this is the cell that is used in hybrid automobiles, such as the Toyota Prius. Those automobiles use a combination of electricity and fossil fuel combustion in an engine to increase the efficiency of the automobile. And this turns out to be quite important. The Toyota Prius, for example, can get equivalent to on the order of 50 miles per gallon in efficiency because of the way it plays electrical power off against fossil fuel-based heat engine power. So the nickel metal hydride cell is worth looking at. The real focus on research, however, addresses the lithium-ion cell. And lithium-ion batteries have two huge advantages. One is that lithium as an element is very light, and it turns out that the figure of merit, the most important aspect of battery design, is the energy content, the energy storage ability per kilogram of weight. And lithium resides right at the top of that performance curve because lithium is such a lightweight element. But the other remarkable thing is that the standard reduction potential of lithium is 3.04 volts. That's a very high standard reduction potential. That means that for each cell in a lithium-ion battery, you produce 3 volts of output. That turns out to be very important. And the thing that the case study does is that it analyzes exactly what's happening in the chemical reactions that are intrinsic to the lithium-ion battery. And so when you look at that, focus on the fact that during the charge cycle, lithium ions move from the positive terminal to the negative terminal, and on the discharge cycle, when the battery is producing power, electrons then move from the anode to the cathode, and the lithium ions simply migrate back across the electrolyte in the middle back to the cathode. So it's a very simple process, but the chemistry of the lithium-ion battery is far from simple, and it turns out developing greater and greater energy capacity per unit of weight is the figure of merit that determines how far, for example, an all-electric car can go on a single charge.